Now, the next session is really interesting because it's going to go in depth into the ESA-ESRIC challenge, and it's going to be chaired by Zaunig and Aidan Cowley. A little bit more about these two people. I'm just opening up my notes here. Frankie recently actually joined ESRIC as a research project manager and previously worked at ESA. And Aidan Cowley currently coordinates the innovation team known as Spaceships, and is based at the European Astronaut Center in Cologne, Germany. And this team frequently works on novel approaches to space resource utilization for exploration. So please, before they come to the stage, please come back into the room with your coffees, with your teas, and give a round of applause, those present, for Frankie and Aidan to explain more.
Hello. They are trickling in, that's fine. So welcome one and all to the session on the Space Resources Challenge. Like it was mentioned, for 2 years at ESA, the Space Resources Challenge was my graduate project, and it was my love and passion. And now I work at ESRIC, where the Space Resources Challenge is my love and passion. Oh, thank you. You might already have heard of a range of other challenges that exist. There's the NASA Centennial Challenges, the X Prize Foundation, or the Sunshot Initiative. They are successful projects around the world, and ESA wanted to get into the game. How can we use this really maturing space resources sector in Europe and Canada to solve the big problems that we're facing in the sector? So, first focus was prospecting, the first step in the ISRU value chain. We wanted to know, oh, sorry, I need to press the button. There we go. We wanted to know, how can we find out ground truth? How can we see high-fidelity maps? Like, we know the satellites can see the resources, but we wanted to ask industry, if you had an imaginary budget and you could do whatever you like, how would you solve this foundational challenge? And we added a few constraints. We asked all our teams to submit a proposal that also would feature a demonstrator, because it's very easy to make up a plan that, especially if you have no constraints and you're allowed to use drones like we have on our logo, or multiple rovers. But really, we wanted you to come to us and show us how you would do it. And even if it's not space ready, the whole hook is that we help you develop your technology further. So, in summer 2020, we opened on OSIP a call for applicants, and we had 36 proposals from industry grappling this challenge, which was more than we expected. And originally, we had space for 10 teams, but then, because the quality was so good, it made it whittling down to 10 virtually impossible. We invited 13. And honorable mention, 3 of them were from Canada. So in November 2021, we made a mock lunar landscape. In the middle of the Netherlands, there's an empty airport hangar, and we added little rocks. We added, as you can see, we added ramps, safe pathways, dangerous pathways, an edge, and a range of resources were displayed in the form of boulders. And the teams were invited to make a map, show us the path they're taking, show us the obstacles, and find the resources and map them and identify them. Additional difficulties, because we are a bit mean, was that the level was very low light, very stark, which makes a lot of cameras struggle. We put a time delay on it because it's on the moon. You have a 5-second delay if you want to directly do it. Try to encourage autonomy. And we didn't let our teams see the landscape. They had to use the technology to explore and map. Out of the 13 teams, 12 actually made it. And that wasn't due to lack of trying. It was due to the fact that we were in a COVID lockdown when we did this field test. Just about managed to get away with it while the Netherlands was in shutdown because it's such a big venue. We only had a few people. But really, the team spirit was there. And we hosted all these teams. They showed us how they performed. And out of them, we had 5... a bit too early. We had 5 winners that we wanted to come back to a second field test. The prize money was in the form of a development contract, was 75K to help mature the technology, and invited them to showcase that improvement at a second, much more challenging field test, which was here in Luxembourg in last autumn. And we have made a short video to show you the second field test, which will be there.
In order to fly to the moon, we need good technology. And if you develop technology step by step, only one company, it'll take a lot of time.
Currently, exploration on the moon is restricted by the need to take everything with us. We can find and extract and use resources on the moon that allows us to support human life for longer periods on the moon. And that's why the use of space resources is so critical.
For this challenge, we create a lunar analog environment. We will create some features that we can see in the lunar surface.
In the first round, we asked them to navigate around obstacles, to take isolated measurements of boulders. In the second round is a much broader perspective we want to address.
The unique factor is really that instead of just asking for paperwork, we asked for a demonstration. They had to overcome challenges in a short amount of time.
Okay. Yeah.
The first phase was important for us because during that time we were able to develop kind of the system, let's say, that operates. It was okay.
We took an approach with, first of all, with several rovers, covering more surface in certain time.
We are a very diverse team with different backgrounds.
It's a hard challenge. There's a lot of uncertainty.
It was exciting to test out our different operational and exploration strategies, and yeah, it was fun. It was intense. We're overachievers. We wanted all the bonus points.
We've collected many ideas in these 2 tests. Innovative ideas we can use in future ESA missions to the moon. And that proves that the ideas can come from companies and research institutes.
That is the right way forward. We need strong Europe on the surface of the moon.
Thank you.
And as you can see, we made a massive lunar landscape again. And after mixing in some ilmenite, our teams got to explore it. Some of them found it. And we asked them to submit a scientific report, a map, and an idea of how they would use the prize money. And now we have all of them here to talk to us about their experience in this challenge. And I have not given them any guidelines. If they want to complain, they may. So could I please have on stage Hendrik Kolvenbach. He's from Team Glimpse, and there was a consortium led by ETH Zurich on their robotic systems lab for the robotics side, and University of Zurich for the payloads. Come on up. Anything you want. Yeah. And we have Tristan Schnell from FCI Robot, the FCI Robot Exploration Team. I'm sorry in advance, Greg. Greg Gawdzik? I'm so sorry. From Team PIAP. And we have Miguel Olivares Mendez. He represents a Spacer S&T and University of Luxembourg and was part of Love Me XR. Sorry, it's a long title. And finally, we have Matt Cross from Mission Control. Come join us. And I will take the chair with him. That's fine. We'll bracket you. So welcome, everyone. Actually, because the presentation ended, it threw me off. Aidan, you have a section about the evaluation and the contract. Could we have the presentation back up? I'll get it back to you. It's not doing it. Oh, the challenge taught us that. I'm really sorry, Matt.
Okay, seems to be stuck, but however, I think we can perhaps proceed, and I can explain a little bit as to why I'm here and what's going to happen next. Oh, there we go. So there we go. Welcome to the panel. As Franziska mentioned, it's really nice to have you all here. I've been quietly watching all the progress in the background, and I'll be involved in the next stage of the competition, which is the awarding of the contract to do more development of the ideas that were presented in phase 2. So the question is, what happens next? And as Franziska was mentioning, we had 5 really interesting teams participating in the second field test. All teams were then invited to participate in a specific tender from ESA. And then from that open invitation to tender, we received 3 proposals from the different teams. 2 of the teams actually merged into one team, which was quite interesting. And then we evaluated these proposals with the results from the second field test as the main weighting factor. So how you performed in that field test was the primary factor for how we actually progressed in the evaluation. So going forward then from the second field test, we will be in a position now to award a winner from this test, and we'll announce that shortly after the panel presentations. And then what comes after that is a technology development contract from ESA for the value of 500,000 euros. Will be placed with the winning team to develop and refine their concept into a further stage of technological readiness, so that we can actually really start moving towards ISRU prospecting on the moon. At this point, I think I'll hand back over now to the panel, because I think you all have to give yourselves presentations. So do we have an order, or should I just go first to second, third, or? You're first, please, come on up. I'll give you the clicker. So.
Great, thanks. Yeah, if my slides come up. So yeah, these are my slides. So also from my side, thanks a lot for joining us, and also to ESA and ESRIC to give us the opportunity to participate in this challenge. I'm going to talk about the legged robotics approach that we took. First of all, I'm talking a little bit about the lab itself, what we do, and then later on what we did for the challenge specifically. So I'm from ETH Zurich, the Robotic Systems Lab. And what we do there is we work on legged robots for exploration. And first, I think it's very important that we discuss why we do this. I think it's always good to have a motivation clearly set before developing solutions. And when we looked in the beginning, what is important for legged robots, where do we see opportunities in space, there were a couple of things that we noticed, like the varying gravity on the different celestial bodies, which plays in our cards, because with the legged systems, they get increasingly efficient with lower gravity. Then the ability to change, for example, the way the robots are moving, depending on the terrain, which gives them some versatility and robustness as compared to, for example, rover systems. And then the advancements in terms of, let's say, overcoming challenging terrain, for example, steep slopes. So this is a picture from the Victoria crater on Mars, which has these very interesting geological features, but is a part that you were, in the past, when you had the rover, were not actually trying to go to, because it was too steep and too dangerous to actually explore. On top of that, there are interesting areas that we don't really know yet how they're going to look like. So we'd have a system that has some overperformance and redundancy in order to basically go there and explore. And on top of that, if you have a legged system similar to also what we do and what animals do, we can use the inherent capabilities of the articulated system to actually investigate the terrain. So next slide is just something what we did in the lab in the past. Maybe we start with the top left video. This was 2019, 2020 on the Rosalind Franklin rover testbed located in Zurich, basically. And on the first day, we were able to go up the steepest possible terrain there. This is 25 degrees. Since then, we have advanced the locomotion controller to really reliably and robustly go up and down the terrain. This was in an actual validation site. And then we developed the systems further up to a point that is starting to become increasingly difficult to actually make the system break. So if you can consider, like the video on the top right, where even additional payload is attached to the robot, we could overcome challenging terrain. And likewise, also here in the field trial, use the system in itself, not only do locomotion, but actually do something useful, in this case, taking a measurement of this rock. So when we heard about this announcement of this challenge, we thought that this is actually a great opportunity for us to showcase our technology also in this challenging terrain. And we formed the team Glimpse, which was led by ETH Zurich and the University of Zurich, and then with additional collaborators, mainly in Switzerland, because not only do we need a robot, we also need scientific payloads, and we need people that support us in this endeavor with engineering and payloads. So what we did is a teamed approach of three-legged robots. So for the first challenge, we just used one robot that we basically duct taped everything to it in terms of payloads. And then for the second round, we made it better. So we can see here three robots with different capabilities. So I think it's important to notice that we have a scout robot that was mainly taking pictures and guiding the other robots to interesting locations. And then we also had, on the very right side, a scientist robot that we call it, with a very, let's say, in situ science instruments, and then also a hybrid robot that could do both for a hybrid approach. So this was work that we carried out, is also now submitted to Science Robotics. The main author is Philip Arm, who is also here with me today for detailed questions for this, because, of course, the challenge here is also how do we operate these robots on the terrain. Here, this is some actual footage from the site, basically going there to the starting booth. You can see all the three robots moving together. This also happened during the challenge. Unfortunately, I don't have footage from the challenge itself, very little what we saw from the robot, because as Franziska said, we are not actually allowed to be in there and see what the robot is doing. So I can show you some footage from what we did after. Basically, after the challenge was finished, here are some demonstrations on the terrain. During the challenge, this is what the robot saw. We can see here the mapping capabilities of the system as it walks over the terrain and starts building up the map. This is what the robot saw. Of course, it's a bit speed up, but here we see like an automatic boulder detection, so doing some automatic science and helping the operator to identify relevant targets. Yeah, this is the outcome then, because the challenge was very limited in time. So we had a couple of hours to not only have all the robots on the terrain, but also get back the data and write a report and present the findings that we actually have on the terrain. So we can see, for example, the map that we created during the challenge on the left side, and then the detailed in situ science, including microscopic images of the terrain, zoomed images of the rocks, spectra of the rocks, so a lot of scientific data exploited in a short time, and then a 200 pages plus report that we created basically on the fly with the exploitation of these results, which I think was a very challenging approach and very challenging for all the people that were involved. So overall, we had all the robots operating on the terrain during the challenge, simultaneously on the terrain. We wrote this massive scientific report with everything that we could find on the terrain. And then also, just something I wanted to add, that key in this success, I think, was also the large amount of development and field validations that we did before that. For us, it was an incredibly good push to perform targeted development. I would say it really pushed the team to get something done. Everybody was incredibly motivated. However, we had to face very monetary constraints. As you said, it was 75,000 euros that we got for all of this. And this, of course, limits also what we can do, because payloads are expensive, and getting them is like, I think all the teams put way more in than what came out monetary-wise. So I think for future iterations it would be great to get more funding, because I think this is an absolutely great way to fund this. Also, we had to, since everything was new, we had to adapt on the fly to changing requirements. So it was a big challenge, but I think it was a great result in the end. So what we want to do in the lab is to push forward. Since more than 10 years, we're working on legged robots. I think we're one of the leading labs in the world on this, and we would really like to see these systems on Moon and Mars, and we are actively working for that. And with this, I would like to thank also my team and everybody here who organized, and also the other participants. Thanks.
Next.
We'll find out.
Oh yeah, they're in order.
Just
perfect.
Put on the slides and we'll see if it's me. That does look like my slides. All right, thank you very much. My name is Tristan Schnell. I work at the ESA-ESRIC, which is a German research institute based in Karlsruhe. And we are actually doing research in all types of information technology. But one of our big departments, which I'm obviously working in, is robotics. And in this, we're doing everything from industry robotics to space robotics. Admittedly, quite a lot of space robotics projects, but as you can kind of see from the title, I want to make sure that you understand everything we are doing is very much transferable to outside of space. We have heard a lot about spin in, spin out, etc. That's why I want to start with a few images of stuff that has nothing to do with space, but uses the same technologies we have used in this challenge. Those are all mobile autonomy applications you can see here, some more obvious, like logistics on the left, or industrial inspection, but even a little bit stranger, like care robotics, which you can see on the right. So all of these have kind of similar requirements, as in we need autonomous robots that are very robust and safe, but also efficient. And how much of these qualities are important in which use case changes a little bit, but all of these always have to be there. Now, I actually want to go to the challenge itself. You have seen what the challenge is about, so I will not go into this, but I want to talk about the approach we chose. Our base idea was quite similar to what ETH chose in the end, a team of autonomous robots. We also had an animal, but instead of having several different payloads, we just brought 3 different robots. And you can see here we had an animal, a husky, and the spot. All of these are commercially available mobile robots, but our system doesn't really care all that much on the robots we use. So we could easily drop in other robots. We also had a little bit of differentiation on what they had to do. We had Animal and Spot as our primary exploration and scouting robots, with the goal to map the environment and find the boulders. And Husky as our primary science platform, with the tooling to find resources both in the ground and in the boulders. Now I'm talking about autonomous robots. What we had in this team was a shared structure of goals and a shared management of these goals between these robots that in themselves, though, were acting autonomously. So every robot on its own decided what it wanted to do and then communicated indirectly with the other robots based on the existing goals. And, which is also a very important part of this, the degree of autonomy we were actually using was dynamically scalable throughout this mission. So we could, in theory, have the system run fully autonomously, including generation of the goals, which included detection of the boulders to then generate further goals to analyze them. But we also had the ability to intervene as an operator on all the different levels. So say, analyze this rock, go to this position, or direct teleoperation with some assistance to actually handle the delay. Now, I want to show what it actually looked like in action. On the left, you can see our base station. So we had one single base station with a single operator, well, at most one operator. Quite some of the time, the robots were acting fully independently. And then we had the 3 robots on the challenge area acting simultaneously. For example, we had our, Okay, we had our spot robot walking around exploring. Continuously animal would also be looking around, and then stuff changes once animal, for example, in this case, finds a rock. Husky, while all of this is happening, our main science platform, would drive around, analyze the ground, looking for resources in the ground. But once a rock is found, it will independently decide to, at some point, schedule analysis of this rock and then analyze it. And analyzing the rock, in this case, meant approaching it, making an image, and then actually taking off the top layer with an angle grinder. All of this using force-based strategies to do it safely. And then on the area we removed, making a close-up picture, and then XRF scan to actually get full information of the rocks. Similarly, our environment was also based on XRF spectrometry on the ground to also get information about the deposits. Yes, and that's the end for me. If you're interested in more of the exact results, just come talk to me. They didn't fit into the slides. Thank you very much.
Okay, I'm waiting for my slides. Hopefully they will come soon. Yeah. Hello everyone, my name is Grzegorz Gawdzik and I represent Łukasiewicz PIAP. And I would like to present you a few slides about our solution, about Space Patrol system. Yeah. But before we go into the details, a few words about my organization. So Łukasiewicz PIAP is an industrial research institute and a robot manufacturer. We are based in Warsaw, in Poland, and since 1999, we are producing the mobile robots. On the right side, you can see a few examples of our products. So we have small platforms like CRM, which you can simply throw, medium size, like Patrol, which we use also in this challenge, that's why Space Patrol, and big platforms like Hunter or Ibis, and they are all on Tyrrell 9. To be honest, it's not our first time on the moon. Before the ESA-ESRIC challenge, we had a few projects with ESA, and two of them were called Racer. It was Racer and Racer CCN1. And during those projects, we were responsible for two things. First one is to create the test site. Second one is to provide the robotic solution, and maybe the third to take the tests, perform the tests. And our goal was to determine the maximal speed during teleoperation with a delay of 5 seconds and limited bandwidth through various types of terrain. During those projects, as you can see, we also use our platforms. During the first one, it was a very small platform called Scout, and during the second project, it was the Ibis platform, quite big one. In this challenge, so ESA-ESRIC challenge, we started with one robot only. So during the phase in Holland, we have only the researcher robot, which you can see on the right side. But during the second phase, so here in Luxembourg in Ash, we used 3 assets. It was the supportive, it was of course the researcher, but the second one was the supportive mobile asset called Scout, and the stationary asset with a pitted camera mounted on top. As you can see, the researcher is equipped with a manipulator and the gripper, and also the XRF sensor to take the measurements of the ground and the rocks. Those orange things, the orange boxes, is our secondary or supportive localization system. Yeah, in terms of our team, it consisted of 5 people. We had 3 operators and geologists on board. On the right side, right now, you can see the view from one of the cameras. It's the view from the front camera of the researcher. So it's more or less the visualization of what operator have seen through the cameras. During the challenge, we used the researcher to take the measurements. So its main role was to take measurements from the ground and from the rocks, and but also make kind of mapping of the area. In terms of the scouts, it was more for exploration. So we used him to take pictures and provide us with information about the environment to know where are the rocks, where are the obstacles, and where we should go. The stationary asset was to coordinate the whole mission. So we wanted to have the visual feedback about the position of each robot and the possibility to coordinate the mission and the goals for the robots. We were quite successful, to be honest. We were able to detect the resource area, the deposit. We were able to map it. We took the measurements from the rocks and explore almost the whole area. So we believe we get some nice results from this project, from this challenge. Maybe I will move forward. Yeah. But unfortunately, there are still things to improve. In our case, we would like to focus more on autonomy, navigation, and localization. And two next things are the collaboration between robots and autonomic sampling. The last two look quite interesting for us, and I believe improvement in both of them will make our solution even better. Okay, it's everything from my side. If you have more questions, please contact me directly. Thank you.
Hello, everybody. So I'm Miguel Olivares. I'm the head of the Space Robotics Research Group here at the University of Luxembourg. And I was part of the LUFMI XR team, yeah? So that was, here we are, a bigger consortium, so in collaboration with the Space Application Services, and then other partners that were supporting us. So the main partners of the team were Space and the Space Application, and also we have other members that were supporting with the scientific sensors. So you can see here, the team was composed by one robot, the big one, the one who was bringing all the scientific sensors. And this was one of the only robots on the competition that was more or less ready for space. So this is part of different European Peraspera projects. And then the small one with the Luxembourgish flag is the 3 scouts that we have as part of the spacer. So the big one is belonging to Space Application Services, and the other 3 ones are from the team of the university. So we basically were constructing a mesh network, working in ROS2. So this is a very novel approach, in where we combining with the lunar lander and the robots, and also the robots from Space Application Services, and sharing all the information in between them. Yeah? We have some issues with the big robots, and we unfortunately have to use the golden ticket because get stuck with the computer, get stopped, and we need to restart it. Fortunately, we were able to go to the moon and switch on. But this using of the golden ticket was penalizing us because, of course, one of the team members have to leave and get in a dark room away from all the others because he saw the environment, yeah? So here you can see what we were detecting with our own lander, the mapping, and also on the bottom part, you can see how the 3 Scout robots were able to do the mapping and merge this mapping. And yeah, so basically, as you can see here, the Space Art team was founded in January 2020, so it's the best thing that you can do when you start a pandemic, to start a new research group. And then, yeah, we were small and not as ready as other participations, but we anyway tried to do as best as possible. Well, just let me introduce the research group. The Space Art Research team is now a big team. So we are 23 people, 12 PhD students, 7 postdocs, running projects on planetary and orbital robotics, multi-robots collaboration, also manipulation in space for in-space assembly or sample collections. And also, we are developing advanced or high-fidelity simulators, digital twin, if you can call it in that way, and applying reinforcement learning in order to adapt our robots to the unknown in the space, yeah? So, well, we have collaboration with 3 different partners, industrial partners, and we managed to acquire 4 million in funding. So, yeah, basically also wanted to introduce that we are organizing a workshop in collaboration with some members here on the panel in ICRA on heterogeneous multi-robot cooperation, and we are also organizing a special issue. So we are open to receive papers if you are interested. Also, I want to say that if you didn't saw in our booth that if you want to put your boots on the moon, we can do it. We have a piece of moon in Luxembourg, just 3 stops from here. So after this session, or after you checking a little bit the poster, please join us to go to the Lunar Lab, and yeah, put your boots on the moon. Okay, so we'll be here the next 2 days, and also my team. So if you have any other question, just please come and ask us. Okay.
Hi, so I'm Matt Cross, and I'm from Mission Control. We are a software company based in Ottawa in Canada. And so as a software company, we are mostly focused in on developing operations software to help missions better develop and better operate their missions. So we're not so focused on the robotics side or the hardware side or the navigation side. We're really very much focused on the user experience and the operations software. And so we took this opportunity to use the Space Resources Challenge as an opportunity to define user requirements for feeding into our operations software product development. And so our core software platform is Spacefarer. And we've been developing this product over the past couple of years and using projects such as the Space Resources Challenge as learning opportunities. So we do a lot of our own in-house testing, but being able to take part in an external challenge really helps define new user requirements, new modes of operation, and just new challenges that we might not be planning for internally. And so part of the learning experience from the Space Resources Challenge has gone and fed into what we now have as Spacefarer, and this will be demonstrated as part of an upcoming capability demonstration, which I'll talk about a little bit later. So our approach for the Space Resources Challenge was to really focus in on working with space hardware companies that have equipment and hardware and sensing that is on a path to flight. So while we do normally use our off-the-shelf rover platform for much of our internal development and testing, we really wanted to focus in on the sensing capabilities. So we worked with MDA, which is a Canadian robotics company. They're known for the Canadarm amongst other things, but also space vision systems. And they have a mid-TRL LiDAR system that is on its path to flight. And so we looked at investigating, incorporating and integrating that into our system, and then developing the interface to support that hardware integration. We also partnered with Impossible Sensing, based out of the US, and they have a mid-TRL path to flight LIBS instrument that we also worked with and incorporated into our system. And so we were really focusing in on how do we integrate and incorporate these sensor systems that are path to flight and may actually be flying in the next few years. And so we want to work with these companies and find the best ways to not only integrate with their system, but then enhance the user experience for these within our system. So our approach to the Space Resources Challenge was really focusing in on the operations and operations readiness and developing some front-end user tools to support the user experience. So we had less focus on the robotics side and the navigation side. We really focused in on tools that we believe will be useful for mission operators in the near term and upcoming micro-rover missions where there may not be the same levels of autonomous operations and capabilities, but really focusing in on what a teleoperator would be doing with their mission. And then we, much like the other teams here, we focused a lot on operational readiness using our own indoor moon yard testing facility. And we use this facility to, of course, do our own internal requirements definition for the product, but also being able to allow external users come in and test it as well. But the most exciting part is so the lessons learned from the Resource Challenge, which fed into our product development, will be demonstrated when iSpace lands next week. So we are a payload customer of iSpace, and so when they land next week, we'll have our capability demonstration, and we'll be using our Spacefarer platform for operating our system and conducting our demonstration. So thank you very much.
Interesting presentations of your time with the challenge. We're now entering into the Q&A session of the panel. I've got some questions, and now Franziska has a few questions. I've got a couple of questions from the audience. Maybe I'll start off myself. From someone who's been watching from the background in a technical sense, maybe you can tell me each from your side what kind of technical challenges you came across that you really underestimated when you came to this challenge, something that really caught you off guard when you actually came to the second phase of the competition. Perhaps starting with Zurich here.
Yeah, I think technical challenge, I think to know exactly what you want to develop, I think is absolutely key. So not only being clear on what are the elements that you want to detect, but also really make sure that you not develop too many features, but rather boil it down to the core of what you want to develop. Because what we underestimated was a little bit the operational challenge of it, because it was very limited time horizon that we had. Which means, in essence, to really make sure that the team is not too stressed and is taking good decisions along the way, you have to practice the operations. And as, let's say, research roboticist, you start to, usually you think of big features, but in the end it comes down to what can you do in like 3 hours of the challenge, and that was underestimated, I think.
Yeah, I think by far the worst thing in the first part, and I'm sure I know we are by far not the only team that had this problem, was the artificial delay and the network conditions. Initially, we knew it was bad. We built everything around it, but we really underestimated the effect it had on the system as a whole and the communication between software components. So this was, in the first field test, definitely the main underestimation on our part.
Okay, my turn. To be honest, I believe we didn't find anything that really surprised us. But we knew that the most challenging part will be the network, because without network, we cannot do anything. We had some experience from the first challenge, where some organizations couldn't run their robots at all due to the network. That's why we created a mimic network at our facility, just to replace it and come here and just start our robots, and it should work. However, there were still some issues on that, and we spent like half an hour on dealing with the network, but we managed. But still, the network was a crucial one, because even the most sophisticated solution would not work without it.
Well, for accounting, we were underestimating maybe many things, yeah. But the collaboration in this big consortium in COVID time was also kind of underestimated, yeah. So we have people in different locations that we never meet in person, and doing something that have to be integrated in rovers and collaborating within robots, and that was maybe a very important point, yeah. And also, well, eventually I sent this question to the organizer about the network, because we have very big issues with the network. So, of course, we were organizing our system in a way that was basically mentioned to be used, but of course, having networks in this huge environment in ESTEC, so in Netherlands, and also in ESH was really difficult for the organization. And that's, of course, yeah, when you have things that was working on your lab and not working on the place, and you have timing clicking, that was really stressful. But they finally managed to solve it, and that was very, very good. Yeah.
So probably the greatest challenge that we faced, and we encountered very similar technical challenges as the other teams. Coming from Canada, our primary challenge was shipping and logistics. We had to ship our system about a month in advance, which did cut down on the amount of technical development that we were able to do in that time. But yeah, the challenges of shipping robotic systems across the ocean are non-trivial, and something we hadn't fully appreciated when we signed up for the challenge.
Well, I think any lunar prospecting mission, logistics might be a challenge, so. Franziska?
Yeah, the network really caught us all out, I think. We also underestimated how much of a challenge we set for you there, which is a good point towards Moonlight, and maybe keep an eye on those requirements. The question I have is that I know I put you through your paces. I saw how much hard work you put in and how much stress there was. But could you tell me about some of the benefits and insights you gained from participating? Like, make me feel a bit less guilty.
So yeah, as mentioned before, the challenge really was a great learning opportunity to test our system and our software in conditions that we hadn't internally planned for. And that really fed into our product development and our capability development. So some of those features that we had to develop for the challenge we'll be demonstrating during our capability demonstration when iSpace lands next week.
Yeah, there was many benefits, so don't feel guilty. There were many benefits at the end. Yeah, during we were not seeing those benefits. But yeah, wow, funny point is that for me it was very nice to test the people I hired for my novel group, but also to push a little bit, yeah, and also to start having things working. I I come in from the autonomous navigation of drones activities, and there are many other competitions very easy to find. Yeah, and I am aware that this competition just push the hard deadline is more than the paper deadline, because okay, for the paper you do the experiments and then you do the graph and good, and the video, okay, but for competition you're going a step beyond, yeah, and then you need to have things working, things running. And of course, demo effort over there, how to solve this last-minute issue. Everything was working 1 week ago, and then the week before the competition, nothing worked. Yeah, so that's, and then this is also very nice, yeah? And then see the relief when everything is working and you did a great job is very beneficial, yeah? And also the team building as well, yeah? Thank you.
In terms of us, I believe the experience for the whole team was very beneficial, which we gained during this 2 challenges, to be honest, because they were really different. For sure, the possibility to develop and test new features, new technologies. For us, for example, we developed the secondary localization system. We improved our autonomy. We created the shared situation awareness system. So many things that we were able to develop and test. That was cool, and probably we will be able to use them also in other projects, in other tests, in other challenges. And yeah, it's added value for sure. And maybe from my perspective also, how the other teams are solving the same issues that we had. So it was very interesting how they manage, what are the possibilities, and to be honest, many of them were quite similar.
Yeah, I would say the most beneficial part to us was the strictness of some of the rules, especially the combination of having no idea what the challenge area would look like and what we actually would have to do, this high uncertainty combined with only one run and no way to interact with the robots during it, ignoring the golden ticket stuff. This forced us to actually build a good control structure and a really reliable control structure where we could and we're actually confident in the end enough to both have them run in full autonomy and to teleoperation, waypoint navigation, and everything in between. But all of this was only, we only did all of this because we were scared kind of what would happen if one of the parts would work, right? So this high degree of fear that was basically created by the requirements of the challenge forced us to actually build a really good control structure, which I think was really helpful even in the future for us.
Yeah, I think I have 2 things. One of them is also about robustness. I think the challenge really forced the teams to build something that is really robust, because you only had one shot, basically, and if you fail, you get 0, and all of what you did was for nothing. And sometimes in research, you write maybe for a paper, and then robustness is not the most important thing. So this really forced us to build robustness and reliability, and this also trained the team in looking for what is the way forward and make the systems robust. And I think the second thing that was really beneficial for us, we got early on also to collaborate with planetary scientists in our team, because coming from robotics and payload experts, so some of the things that we integrated in the systems were really a little bit out of our expertise in terms of how to analyze samples, for example, that you get from rocks, know really what is important there. And I think if there wasn't a challenge, I think we would have not onboarded these people, and I think we learned collectively a lot from this experience.
Okay, great. I'm conscious of time, but I do have one question I'd like to throw to the panel that came from the audience. I think it's an interesting one, and maybe there's no answer to it, but did any of your robotic systems see any significant wear or damage from the actual first or second challenge phase, especially with the dusty environment?
So I think during the challenge itself, not so much, but in the process of getting there, like the various shakeouts and field trials, of course there were many failures, like the robot braking, electronics braking, and many things like that, because of the development in the short time, just break on the way. But during the challenge itself, there was no significant issue.
Yeah, I would also say there was no real wear and tear type effects during the challenge. I have to say that in the first challenge we crashed one of our robots and something broke, but I think that's something very different than what you were talking about.
Definitely.
The actual wear and tear was negligible, but we also had dust-protected robots, so dust specifically really wasn't a problem because we planned for it.
I think that during the second challenge, we didn't have even a scratch. So no issues on that. During the first challenge, there was kind of a steep platform, I would say, and when we were crossing those platforms, it was a bit tricky because we were like on the peak of it, and our platform weighs like 100 kilograms, so it was. And we have the 5 seconds delay, so the passing through this peak was quite scary, but no issues on that. Thank you.
Yeah, on our side there was not damage, big issues. Yes, of course, removing the dust. But I also have to highlight that the small rover that you saw in the presentation of Frankie and of my presentation, it's kind of a research academic robot. Yeah, it's a 4,000 euros robot. And that was performing amazingly, yeah. So that's is all the contrary, not damage, and even performing really great with this a robot that, by the way, is a Leo rover from a Polish company, yeah? And that was performing very, very well, yeah. So we were, on the contrary, very, very satisfied with the performance.
So there was during the first field test, the time to complete the challenge was 2.5 hours. Yeah, correct. And during the first field test, it wasn't so much wear and tear, but we definitely wore down our battery very quite significantly during that first field test, and so we had to upgrade our system. For the second field test, where it was a much longer duration and we had more equipment connected to our system. So it wasn't so much wear and tear, but needing to do some more system upgrades.
Okay, great. Well, thank you all for the answers from the panel here. I'm now going to move on to the next stage of the presentation, which is to announce the winner from our side. So just give me 1 second to stand somewhere slightly more official. It is a pleasure on behalf of the other side of the team of the ESA-ESRIC people who've been organizing it to be able to present this particular slide now, so hopefully it comes up. The pause is not dramatic, it's technical, yeah. So the chosen team for the next stage of the ESA-ESRIC challenge is ARISE. So the Autonomous Robots for In-Situ Surface Exploration, and this is the combination of ETH Zurich and FZI. So please, congratulations and a round of applause. Of course, it's a larger consortium as well. The University of Zurich, University of Basel, and University of Bern are also engaged in this consortium, and we're very much looking forward to working with you guys on advancing your technology and developing it for in-situ resource utilization prospecting on the moon. And as a small little gift of appreciation from our side as well, we have these little keepsakes for yourself and for your team on the side here to take home and give to yourselves and your team members. Proprietary ESA technology on the moon part there, so you can try reverse engineer if you like. But thank you very much for your participation in this challenge. It's been really excellent to see all the performance, all the teams, and all the really interesting technical innovations and what you brought. Each team brought something different, and it was really excellent to watch it. We're not quite finished yet because my colleague Franziska now will present some more information. We're almost done. So Franziska?
We have a few minutes to point towards the future. Do you want to hit the button? Okay, we'll get there. Right, we are announcing to you all that this challenge was such a success. As you've heard from our teams, they enjoyed participating. ESA and ESRIC both enjoyed the experience. We want to continue doing this. Maybe I should have mentioned very clearly, this was the first time at ESA we've run a challenge, and happy with the outcomes. So now we're looking at creating more. We don't have to focus anymore on prospecting, the very first step in the ISRU value chain. The whole value chain is open to you. And we're asking you, as the experts in industry, what areas do you see could use creative, innovative, large-scale solutions? And today, on ESA-OSIP, we have launched a call for ideas. And it is literally asking you to submit either challenges itself or large-scale problems. You can also suggest if you would like to host one of these events, or if you have resources you could provide. This is really a community survey. We want to see what problems you would like to see solved. And then the idea is that over the next few years, we will be running continuous challenges. All of you are invited back. Please come back. It was great working with you. And hopefully we'll solve all the big problems that Space Resources is not yet facing. So there is a QR code for you. You can take a look. The timeline I'll go back to. The challenge will be open until the OSIP portal will be open until the 30th of July. After which we'll spend some time reviewing and then make a challenge roadmap, hopefully lasting the next 10 years and beyond for Space Resources. And every year at the Space Resources Week, you will see either hear an announcement for what the next challenge is, or meet our competitors and hear the winners. And this will hopefully become a staple in our community. So please submit your ideas to our call for ideas. It's live. Okay, we're done. And at the ESA booth, there are people ready to answer any questions, or you can flag me or Aidan down. We'll do our best to guide you. Yeah, great.
So please, we can disband and let the...
Yes, we have also made some certificates for you, but we can do that off stage.
Thank you, everyone.
Thank you.